Hi, I'm Alan,
I'm Philip.
and we're here to present our project HawkEye. So self-driving cars is a very hot topic right now. It's got a lot of potential to reduce traffic accidents and congestion. And as engineers, we want to figure out how the car sees the world, and it's very exciting for us because machine learning plays a big role in that process. So specifically for our project, we're going to be taking in LiDAR data, which I'll talk about later, to detect cars around their central car. The overall software will hopefully be incorporated into a pipeline in UFT self-driving car. It'll take in data about 10 hertz. It'll pre-process the LiDAR data into usable form, and our neural network will take in that data to output bounding boxes, which will be fed back into a path planning module and back into the car. Two sources of data. There's a pre-labeled Kitty object detection data set that has about 7,000 frames of road images. We're just using this to, so that we don't have to label so much data. We use this for train and validation. To test, we collected about 200 frames labeled by hand from UFT's car Zeus. So very quickly, what is LiDAR data? So as you can see, it's a 3D sensor that scans the 360 degrees once. And as it does, it shoots out rays and it returns reflectance values if it hits an object. So as you can see, it hits an object there and creates those LiDAR points. So if you put it on top of a car, you can kind of see the shells of all the objects around the car. To prepare this kind of data, we take slices along the height and treat each slice as a 2D image. So altogether, you have an image with many, many channels. And we can feed this into your traditional CNN. To visualize this data, we compress all the point clouds onto one bird's eye view representation. And this way, we can label cars on bird's eye view. So this is a test data that we labeled. The left is the camera shot from the car. And then this one is the compressed bird's eye view point clouds.
Yeah, so as you see, as we roll the video, we put bounding boxes on those cars and the pedestrians.
Mm-hmm.
So our neural network model is inspired by a design from Uber ATG in Toronto. The first part of our network is a ResNet backbone. It is made of over 50 convolutional layers, and each layer is containing a bunch of 2D convolutional layers, batch storm, and ReLU activation functions, organized in this ResNet block, which allows us to train such a deep neural network very, very efficiently. We use this architecture called feature pyramid. So basically, we take our input representation, and then we downsample it first, and then we upsample this feature map to get a higher resolution feature map with more details. In total, our network has over 1.7 million parameters. So building on top of the feature map generated by the backbone is a header network. So there's two parts to the header network. The first part is a binary classifier. It is essentially made of a series of convolutional layers and a sigmoid function, and it predicts a confidence. So this confidence represents on every pixel on our feature map whether this pixel contains a car or not. The second part of our header model is a regressor. A similar architecture, but it predicts the dimensions of our bounding box, essentially the heading of the car, the centroid of the car, and then the dimensions, the length and the width of the car. So during training time, we applied the smooth L1 loss function to our regression branch and binary cross entropy function loss to our classification branch. So here are some of the results of our training on the validation set. So we managed to achieve an average precision of over 60.7%. Our network, as you can see on the precision recall curve, it is very precise in this regime. This tells that our network it doesn't have a lot of false positives, and that's a good thing. But however, as you can see, we only have a max recall of about 60%, 67%, and that means that that's an area we could potentially improve on because there's a lot of false negatives that we did not pick up, and we don't want our self-driving cars to run into a pedestrian or a car because we didn't pick it up. Our network runs on 15 milliseconds on a GTX 1080 Ti GPU, meaning that we can run this inference in real time. So I'd like to share some of the techniques and tricks that I used we found were very helpful to our training. So in our setup, we use a NVIDIA Tesla V100 GPU on Google Cloud. We created a custom C++ preprocessing script that takes the raw LiDAR point cloud and then turned it into bird's eye view representation very, very efficiently in training time. We heavily use this PyTorch's multi-processing module, and with all that stuff, we were able to achieve about 6 minutes per epoch in training time. Weight initialization and backstorm are the two things that we found really useful when we were training from scratch. We use stochastic gradient descent and momentum to help us train. And then we also incorporate TensorBoard into PyTorch, which allow us to visualize our training process when we are training on the Google Cloud server. And if we see, for example, if the validation loss of validation area starts plateauing, we manually decrease our learning rate.
This is a visualization on the Kitty dataset, the validation. On the left is, again, the camera frame. On the right is the outputted bounding boxes on the point clouds. So as you can see, it tracks the nearby cars pretty accurately, and as it turns, it also keeps also keeps track of it turning, and then you can see that it still keeps.
Yeah. So as you can see, our detector is pretty consistent.
Then
Yeah, even though it's not using any history of the information, it's only
Mm.
detecting on every frame.
So on the test data, it's where it starts getting weird. So around the car, you see a lot of false positives. And there's many reasons this happened, but possibly it's because of hardware issues, because the hardware calibration is not really the same with the kitty. So there's a lot of false positives there. For the project, our key learnings is that software engineering is key. So you want scalable pipelines so that when you switch between testing, training, and validation, you don't have to change too much code. Data labeling was a bit tedious, so perhaps we shouldn't have tried labeling our own data just for this project. And of course, the difficult problem of detecting pedestrians. And it was hard to incorporate the pedestrians into the network, so perhaps we shouldn't have framed it for pedestrians and cars, just the cars. And that's it.
Great, that's a ton of work. And it seems pretty successful. I would guess the fact that you trained on different data and then you tested on finally, that's got to be some of the problem, right?
Some of the problem, except we kind of did that on purpose, just because you don't want to have to retrain a model for every new batch of cars that a company or different companies will produce. So with that in mind, you don't always have the chance to mix in your testing data with your online kitty data set, right? So we did, but perhaps for this, we might have to.
If you did train in the real world, you would be forced to make sure that the data you're training on is what you would expect. And so that would be okay. It would have been okay to mix those, I think. But it's hard work to do the labeling. Question about just in the actual functionality. Back to you talked about where's the model? Back here.
It's next.
The model is
Yes. Next slide.
next slide.
Next.
And next slide.
It's coming up.
And one more, yeah.
Here.
Maybe it was, here, back at the so you have a classifier, you classify every pixel, but
Every pixel on the feature map. Remember the feature map, the size of feature map is downsampled from the input.
and so did you have to not still group some of those together? And is that what the regressor does? It groups a bunch together, or just
No, the regressor predicts, like say if the
given that classification?
independent, but when you actually run the inference, you use the information from the classifier first. If it's very confident, then you look into the regressor. The regressor tells you the dimension.
Oh, okay, that makes sense. I get it. Cool. And just plugging TensorBoard into PyTorch, how hard was that?
It was hard at the beginning, but it was easier than I thought. Let's just put it this way.
Yeah, I was tempted to try to make that happen for everyone, but didn't.
Yeah, I think it's
doable.
very, very useful. TensorBoard is one of the things that we found that when you're training on a cloud server, especially when training takes so long in the beginning,
You just keep an eye on it.
you keep an eye on things and it records it. It's very convenient and you don't have to write a lot of code. It generates a plot for you. And
Yeah, I've used it. It's great. And that's what I was thinking about. So next time I think I'll try to make that available. Cool. Questions?
You mentioned that one of the key learnings was that you should have only done cars rather than pedestrians. If you had a lot more time to work on this, do you think the current approach would be realistic in expanding out to more and more different types of classifiers, like beyond people and cars potentially? Or do you think the approach is fundamentally limited and you'd have to do something else?
For this model, I don't know if it's because the paper only presented it on cars.
yeah, but I think this model, it can extend to pedestrians and cyclists, but I'm not sure if for any other more. But remember, this network is designed for self-driving cars, so you're only trying to detect those common objects on the road, not necessarily common everyday objects you see in a
So
classroom.
it might not detect a bird suddenly flying into your car.
Probably not.
Probably not.